Hello everyone, welcome back to the video lecture series. In today's video, we are exploring total and effective stress analysis in finite slopes, a key concept in soil mechanics and slope stability. This topic is part of Unit 5 for 5th semester civil engineering course, Soil Mechanics at SNS College of Technology. Let's begin our journey into understanding how slopes behave and how engineers ensure their stability. Let's recall before we dive deep into the topic. Let's take a quick recall. We have previously studied soil shear strength, shear parameters, and slope basics. In this session, we will connect those fundamentals to real world slope stability, especially how total and effective stresses influences slope failure. The topics for discussion in this video we will cover what infinite slope is, types of slope stability analysis, total and effective stress concepts, methods of stability analysis, examples and applications. So what is an infinite slope? A finite slope is one with a specific limited height, like the slope of an embankment, a highway cutting, or the side of a canal. These slopes generally fail along circular or planar surfaces. The major goal in analyzing them is to determine the factor of safety, which tells us how stable a slope is against failure. The type of soil and drainage conditions determine whether we use total stress or effective stress analysis. So why to study slope failure mechanism? It is important for engineers to understand slope failure because slope exists everywhere from road embankments to dam structures. Poorly designed slopes can lead to landslides, erosion, and even catastrophic failures. A good understanding helps us ensure safety, minimize cost, and predict behavior under rainfall, earthquakes, and loads. In the context of design thinking, the first step is empathize. Here we empathize with the problem by observing slope failures, understanding soil behavior, and identifying the factors that leads to instability. This helps us design safer slopes and protection measures. Next stage is define stage. The define stage focuses on creating a clear problem statement. In slope stability, the defined objective is to identify, analyze, and classify failure mechanism so we can ensure long-term stability of the slope. Next stage is ideate. In the ideate stage, we generate multiple solutions. In slope engineering, this means exploring different methods like total stress analysis, effective stress analysis, stability charts, and numerical tools to find the most practical and safe design. Now let's understand the core concept. In total stress analysis, it is also known as C analysis, is used for short-term and undrained conditions, typically in clay soils. Here, pore pressure is assumed to be zero immediately after the loading, and cohesion alone contributes to the shear strength. In effective stress analysis or C5 analysis, it is used for long-term drain conditions like sandy soils or slopes subjected to slow loading. This considers pore water pressure effects, and both cohesion and angle of internal friction contribute to the shear strength of the soil. Choosing between total and effective stress analysis is crucial because wrong assumptions can lead to unsafe designs. The factor of safety tells us how close the slope is to failure. If factor of safety is more than 1, the slope is stable. If it is less than 1, failure is likely. The factor of safety depends on shear strength, slope height, soil parameters, and pore pressure. We use different methods to analyze the slope stability. First is Swedish circle method, a simple method assuming circular failure surface. Next is modified Bishop's method. It is more accurate as it considers interslice forces. Next is Taylor's stability chart, a graphical method used especially for cohesive soils to estimate the factor of safety without complex calculations. Each method has its own advantages depending on soil type, geometry, and level of accuracy required. Next is Taylor stability chart, a graphical method used especially for cohesive soils to estimate the factor of safety without complex calculation. Each method has its own advantages and disadvantages. In Taylor stability charts, it is used widely for cohesive slopes. The concept uses a stability number which is calculated by dividing the cohesion of the soil by the product of density into height of the slope. From this, we can find the factor of safety using the chart based on the stability coefficient. These charts help determine the safe height of slopes and are useful for preliminary design. Drained versus undrained condition. It is essential to distinguish drained and undrained condition. In drained cases, like rapid loading on clays, pore pressure doesn't have time to dissipate. We use total stress analysis. In this case, long-term stability of sand slopes or slopes under steady seepage, we use effective stress analysis. Understanding this distinction prevents errors in design. Real-world applications. You will see finite slope design in many places. Road and railway embankments, earth dams, retaining structures, village and hillsides. Each of these must be analyzed for seepage, loading, rainfall, and soil type to ensure proper safety. To summarize, finite slope stability ensures safety and reliability of engineering structures. Total stress is used for short-term undrained conditions, while effective stress is used for long-term drained cases. Different analysis methods help us calculate the factor of safety and design safer slopes. So, curiosity challenge. Here is a question for you. A 6-meter slope with an angle of internal friction 30 degrees fails after rainfall. Which analysis you would use, either total or effective stress? This is assessment. Question 1. What is the difference between total and effective stress? Question 2. In drain conditions, which parameter governs shear strength? So for first question, answer is option A. Total includes pore pressure, effective excludes it. Second question is option B. C dash and phi dash. So the reference for the above topic, the web links are provided. You can refer to the above web links. So thank you for listening to this video patiently. Have a good day.